Alright, here's a quick rundown of some of these Greek letters we're going to see in chapter 12. We got here a cylinder, and we're looking down the length of it. And we are going to apply a torsion to it. So that's our first letter we'll look at, the torque. And that results from some force being applied with a moment arm, which is that distance from that force to the center of rotation. So we've seen that one before. That torsion then causes a kind of twisting of the cylinder. So let's say it's held fast at this end over here, and this end will twist a little bit. So let's look at the angle of our twist here and call it phi. So this angle is called phi. And this is not the angle that describes the shearing stress, or the shearing strain. To understand that angle, we have to look at the cylinder from the other perspective. I just set it on its bottom here. So this is the angle phi. Alright, we got our bearing straight. Alright, good. Let's look at the outside of this cylinder. I'm going to draw one line up to that point and another line up to that point. And the angle that those two lines make is gamma. And that is the pretty much equal to the shearing strain. I say pretty much equal because technically the shear strain is equal to the tangent of that angle gamma, but in real life situations this angle is going to be really small, so the tangent of gamma is pretty much equal to gamma in the situations that we look at in real life. So we just looked at gamma on the outside of the cylinder. Let's look at it on the inside. If we go back toward the middle, we can see that the angle decreases. So I just drew a little dot here to be like the middle of the cylinder. If we go from really close to that and then draw a line to straight up through the cylinder, two lines straight up through the cylinder to go to either side of this angle here, we find that toward the middle of the cylinder this angle gamma is a lot smaller, which of course means a smaller shear strain. And in any case, with any cylinder, no matter how much shear stress is on it, if we get actually at the middle, then gamma is 0, because both lines go up just to the middle of the cylinder at the top. That angle is 0 and the shear strain is 0. So we've found that the shear strain goes from a maximum value at the outside of the cylinder to a value of 0 at the inside. It's kind of like getting an Indian rug burn on your wrist. That skin is going to feel like it's shearing on the outside, but the middle of your wrist doesn't get sheared as much. So again, that angle, that shear strain is gamma. That's different than G, which is the shear modulus. This is like the elastic modulus, like Young's modulus E. And just like E is stress over strain, G is also stress over strain, but it's shear stress. This is tau for shear stress. We've seen that before. And the shear strain gamma that we just found. So that big G is the shear modulus, or the modulus of rigidity. And let's look at one more letter, J. And that's the polar moment of inertia. I'm not sure what to say about this beast J, polar moment of inertia, other than it's another number that gives the resistance of an object to shear strain. This J kind of makes sense if we think about trying to shear a pipe. So if we apply torsion to this pipe, apply shear stress, it kind of makes sense that the thinner the pipe walls, the more resistant to shear strain it's going to be, the less it's actually going to twist. So that thickness of the pipe is reflected in the definition of J here. So the DO is the outer diameter, and the DI is the inner diameter.